with me. Okay, so we're going to talk about modern ciphers. And we're going to talk about something called public key encryption. And this is the way we typically do cryptography on the internet today. And so I'm going to recap what you've learned so far. We talked about yesterday the different kinds of ciphers, the Caesar cipher, the substitution cipher, and the transposition ciphers that you could use to scramble a message. And the idea is to apply some simple shuffling functions or transformation functions. And we saw that each one of these has problems. You can easily reverse these things to find out what the plain text is. And then we went to more complex schemes, the Vigenère and the Enigma. And so these are much more difficult to crack. But the one thing that we saw, especially with the Enigma, is that you have to distribute a whole bunch of secret keys in order for the two ends to communicate properly. And as it turns out, operationally, that was really hard to do. Sort of like the Zimmerman telegram from the beginning. If you capture the code book, you've got all the messages. If you capture the key sheet, which you all had last night to do the homework, you can decrypt any of those messages even though they're encrypted. So this key distribution problem motivates public key encryption. We want to get rid of that problem of distributing a key. And so all these schemes that rely on public key cryptography simplify the key distribution problem because it gets away from needing that shared secret key. For example, the Enigma settings, or in the Vigenère, that fixed key that you're using to select the alphabets, like CyberPDX or PSU. You don't have to do that, so that means the adversary, the eavesdropper, doesn't have a chance to listen in and capture the keys. Okay? So there are two parts. There is a public key that you broadcast everywhere. Everyone knows this public key. And the special thing about this public key is that when someone uses it to encrypt a message, the private key associated with that is the only thing that can decrypt that message. And you keep that private key secret. And that's how it works. I'm going to show you what sort of the function of this using an analogy. So the public key in this case is like distributing an open lockbox, an identical lockbox, to all the people who might be sending you a message. And you hold the only physical key that can unlock that lockbox. And so you throw all these lockboxes out in the world, they're all open, someone needs to send you a message, they throw their message in the lockbox, they close it, scramble the combination, not scramble the combination, but close it, lock it, send it back to you. Nobody else can get into that lockbox except you because you have the only key. This is functionally what public key cryptography does. Okay? So this is what happens. The recipient broadcasts that public key across the internet, keeps the private key associated with that secret, and then if a sender wants to send this recipient a message, it takes that public key, encrypts the message with the public key, sends it to the recipient, and then the recipient, because they have the private key, can decrypt it. And no one else in between can do the decryption. Okay. So the decoding of a message without a private key is assumed to be prohibitively expensive. And the way we make sure of that is that we rely upon a known difficult mathematical problem that is hard to perform. And so the eavesdropper has to do a lot of math in order to decrypt that message without the private key. So here's a question. So this is securing everything. There's a specific hard problem in math that is securing all of our transactions right now. And which one is it? It is factoring a product of prime numbers. So that is the hard problem. Let's see if my Frisbee skills are, oh no. Sorry, I'm gonna grab that. That's correct. So it is factoring a product of prime numbers is the difficult problem that all of the internet transactions rely upon. So any time you see these green lock icons in your web browser, It is validating the public key, private key authenticity of that transaction and giving you that symbol. So that's sort of the underlying principle that's protecting that. So factoring products of large prime numbers is the problem. What happens if someone figures out how to do that, right? Yeah, the world breaks. There's a lot of things that are unhappy with that problem being solved. So all of your transactions are probably not going to be as easy anymore. And unfortunately, this is one of the problems that quantum computers can easily solve. They know that they have a formulation as soon as a quantum computer is sort of developed, a sufficiently large one, they can crack RSA. RSA is the algorithm that is based on the factoring of large prime numbers. Okay? So, we need something that is resistant to a quantum computer. And so, in the last decade, the NSA and a whole bunch of researchers, a lot of mathematicians, are developing algorithms for a post-quantum world. What happens when you have a quantum computer and need to secure all those transactions? That's what that is about. So if you see that in the news, post-quantum cryptography, this is what they're talking about. How can I get an algorithm or an underlying mathematical problem that is resistant to a quantum computer? Okay, so there are these strategies that people throw out there. Elliptic curve was one of them, and in 2015, the answer was, yeah, that's resistant to a quantum computer, but then some clever person figured out how to break it, so now the NSA says no. There's this lattice problem that they were like, yeah, no quantum computer can solve that. Initially, yes, but then we just hired a faculty member here at Portland State who was one of the key people of breaking the lattice problem with a quantum computer. So this is something that's ongoing in this country. Okay, so I am not going to have you try and factor products of large prime numbers. I'll spare you that. I am going to show you a different hard problem just to conceptually get your mind around how this thing might work. And so the analogy here is that the ice cream truck problem, which I'm going to introduce, is going to be similar to the factoring the product of prime numbers. So let me talk about the ice cream truck problem. This is the other name for the ice cream truck problem is the dominating set problem. You have a graph, and for example, we'll take a map of a city, and in this map, you have circles, which are neighborhoods of the city, and you have lines, edges, that are roads in between the neighborhoods. And the problem that you want to solve is to cover the map with a minimal number of ice cream trucks with the following condition. Every neighborhood in this graph either has an ice cream truck in it or is directly connected to one node with an ice cream truck in it. Exactly one node. And this is the dominating set problem. So that is a graph. And I want to give you an activity. The first activity of today is to find the dominating set for this graph. How can you arrange ice cream trucks in this map so that every neighborhood either has an ice cream truck in it or is connected to exactly one neighborhood that has the ice cream truck? So I have the handouts here. One per person, actually. And on the table, you see chips or pasta. You can use whatever color you hopefully use for the ice cream trucks, use the color that has the least number of items in the cup. I wasn't very good at distributing them. And if you need more props, I've got some up here. So yeah, one per table and then one sheet per person. Okay, I'm going to pop up the solution, and you can rejigger your chips to match it, so that you can show to yourself that a solution does exist that meets these constraints. And those are the nodes. That is the dominating set for this graph. So every neighborhood in this graph either has an ice cream truck in it or is next to exactly one node with an ice cream truck. Okay. So take a look at that. Okay, we're going to continue. That was all fine and good, but we got to use this for something, right? So we're going to use this graph for encryption. But first, what I'm going to talk about is your homework, one of your homeworks. Actually, no, I'm going to talk a little bit more about this graph. So these are the 8 nodes that dominate this set. How can you prove that a solution with 7 doesn't exist? Yes? A prime number? You can use properties of the graph that, so similar to prime numbers, but you can use a property of the graph to ensure that no other solution exists. And this is what we're going to talk about. So you prove this by constructing the graph yourself from something else. And what we're going to do is we're going to throw out a bunch of ice cream trucks, directly connect them to neighborhoods, and then what we're going to do is we're going to create a graph that just connects the outer neighborhoods to each other. And so we're going to add links to this graph that go in between neighborhoods and not between ice cream trucks and other neighborhoods. And so if you look at these 2 graphs, you see that the edges that we add are between 2 neighborhoods without ice cream trucks in it. And so with this graph, you still have those 8 nodes dominating that graph. Okay, but it's obscured, right? You sort of like, you took an easy graph and then you put a whole bunch of arcs in it, and then it makes it hard to determine what the dominating set is. So that's the idea. And this is what we call the private key in this particular problem. So that's your private key, is the dominating set for that graph. And what you do is you take away the nodes that are your dominating set and you publish the rest. This is the public key. And we're going to send this public key everywhere. So this unlabeled graph goes to everyone who wants to encrypt a message and send it to us. So your homework is to find the private key of this graph. It looks way harder than it is. We put like a little bit of a backdoor in there to make it a little bit easier. And so if you struggle with this for more than, I'll give you 30 minutes, you can come to me and I'll give you the sort of the thread that will unwind the whole graph. But that's intentional. We stuck that in there intentionally so you wouldn't have to spend hours and hours on this graph. But the purpose of this homework is just to give you an appreciation that if you wanted to scale this problem to be extremely difficult, that you couldn't solve in just like 2 or 3 minutes, you can easily do that. You just construct a bigger and bigger graph, and then the person who has to decrypt that message has to do a lot of work. And that's the intent of the homework. Okay? Once you get a solution to this graph, come and see me during office hours, and I'll give you some wristbands. Or tomorrow. It might take you until tomorrow to solve it, so just find me and show me your solution. I'll give your team some wristbands. Okay, so now we're going to have to do something with this problem. We have a public key and a private key. How the heck are we going to encrypt a message, data, from a sender to a recipient with this public key? So we're going to use the ice cream truck problem to encrypt some messages. Before we do this, we have to set up a story. The story is of Bob, Alice, and this adversary, Evan. So Bob has a message for his mayor, Alice. He's a concerned citizen. And he wants to send this message to Alice without Evan knowing what this message is. Evan wants to listen in and eavesdrop so that he can see what is being sent. But neither Bob or Alice want him to listen. Alice is the mayor, and she wants to hear from concerned citizens like Bob. But the problem is that Alice has never met Bob, doesn't know who Bob is, but wants to communicate securely with Bob. How can this happen? Well, just like before, She's going to create a public key and a private key, and the public key is like the open lockbox, and the private key is the key that can unlock that. And you would like to send that public key over to Bob, have Bob write the message in, throw it in the lockbox, shut it, and send it back to Alice, and then Alice is the only person who can decrypt it. So that's what we're going to try and do. And we're going to do this using that ice cream truck graph that we're just working on. And we're going to use a very simple ice cream truck graph, just so that we're not here until after lunch doing this exercise. So, as before, we're going to do this by construction, right? We're going to put some ice cream trucks down, connect them up to directly to the neighborhoods that they serve, and then we're going to apply some edges between neighborhoods in order to keep this as the dominating set. And then what we're going to, so this is Alice's private key now, right? This graph with the nodes that serve as the dominating set is the private key. She's going to unlabel all of that, and that's the public key. And this is the public key she broadcasts everywhere on the internet. And then Bob gets this public key and wants to encode a message. And so we're just going to do a number, a single number. Bob is going to send from himself to Alice. And the number we're going to send is the ASCII representation of a character. So he wants to send, say, hello there over to Alice. And so what we're going to do in this example is we're going to look up in our ASCII table and look for the number that represents capital H in ASCII in a decimal format. And so decimal 72 is the character H in ASCII. So we're going to try and send the number 72 very securely from Bob to Alice. So that's what we're doing. So Bob gets a copy of this public key, and he's going to run an algorithm. And the algorithm he's going to run is he's going to create this worksheet that's based on this graph, where he takes that public key and he fills it with a bunch of random numbers. And the random numbers will all add up to 72, that letter that he wants to encrypt. So 72 is capital H. So he makes sure that those random numbers add up to 72. And this worksheet is the unencrypted message, right? Because if Evan got a hold of this worksheet, all he'd have to do is add up the numbers in the graph, and then he's got 72. So this is not what you're going to send. Instead, what you're going to do is you're going to take this worksheet, and so you can validate this offline. If you add up all these numbers in this graph, you'll get 72. You're going to take this worksheet, and for each node, he's going to add up all the numbers that are connected to that node, including itself. So here's an example. Down here, you have this node 0 that has a 0 value in it. 0 plus 7 plus 6 plus 5 is going to give you 18, which is part of this other graph. So that is the algorithm that he follows for every single node in the graph. And so, for example, this node here in the upper left is 6 plus 6 plus 7 plus 7, and that should give you 26. So that is what he's going to do. He's going to take that worksheet, which is unencrypted. He's going to run this algorithm, and this is the encrypted message. He's going to take this graph, send it over to Alice. So that's the encrypted message. Now, if you are Evan, you get this encrypted message, and what is the number that he's going to figure? Can he figure out what that number is? What problem might he need to solve to figure out what that number is? So it turns out this is really difficult to solve. But Alice, because Alice has the private key, the only thing Alice needs to do to decrypt this original message is to overlay her private key onto that graph and pick out the dominating set. And the dominating set here are these 3 nodes. She adds up these 3 nodes, and she gets what? 72. And that is just the way we have structured the dominating set, and we have calculated the sum of the neighbors and placed it into each node. And because Alice knows the dominating set of that graph, all you need to do is go to that set, add up those numbers, and you have the original message. You have the original data that you were going to send. Is that clear? Okay, so if that is clear, well, why does this work? So, in order to decode these messages, Evan now needs to figure out what Alice's private key is. He has to solve that dominating set problem, usually. And so I am going to give you a turn at doing this. So this is the last activity of today. And the activity is an important message has arrived from outer space. Each of you will get a single character of this message. It's been encrypted. You'll get a single character of this message, and what I want you to do is find the dominating set for this graph, add up the numbers for the nodes that are part of the dominating set, figure out the ASCII representation for that number. So, did you bring your ASCII table? I'll put one up so you can look at it. Actually, on the crypto website, there's a link to an ASCII table, so you can bring it up on a computer as well. And then what you're going to do is you're going to generate the ASCII character for your own message. And as soon as you generate your character, you're going to try and figure out what the other 52 characters are by walking around and trying to get these characters from other people. And as soon as all 52 characters you've gotten the message decoded, come up and tell me what that message is. And your target is 15 minutes. It should take you around, well, hopefully under 15 minutes to do this exercise as a group. Okay, so I have the activity here. You're going to get a packet, one per table. And each packet has 6 sheets. So grab one sheet, figure out the dominating set, add up the numbers, and then generate your ASCII. Thank you.